Okay, today I'm going to solve Leetcode number 45, Jump Game 2. I just solved Jump Game 1, which is right here. It was fairly straightforward, but I've not seen the problem statement for Jump Game 2 yet. The purpose of this video and any potential future videos like this one is to practice for technical interviews by talking through how I solve problems. So let's take a look at Jump Game 2. I'm going to read the problem statement. Alright, so it's fairly similar. You're given um, an array of maximum lengths of forward jumps. Return the minimum number of jumps to reach nums in minus 1. The test cases are generated such that you can reach nums in minus 1. So before, where we were trying to figure out whether it was possible to reach a certain point, now we have to figure out the optimal way to reach that point. So let's look at some examples. So for this problem, the minimum number of jumps to reach last index is 2. Jump 1 from 2 to 3, and then, or from index 0 to 1, and then all the way to the end, because you can get 3 jumps there. So I guess the tricky part would be, in a greedy solution, you would want to jump the furthest you can at each point, but that would lead you to an unoptimal solution, because you'd want to go from 0 all the way to 1, or all the way to 2, but then you could only go 1 at a time, so that would be more jumps. So the naive solution of picking the furthest jump at each point will not work. Example 2 is fairly similar. Actually, exactly similar. You make the same jumps, you just don't fall into the 0 trap. So let's think. The test cases are generated such that you can reach it, so we don't really need to worry about 0 traps. We just need to make sure our optimal path doesn't fall into them. So I guess one way of thinking about it is at every stage we have 2 options, or not 2 options, however high the value is options. We can go the max distance or we can go something less. So for 2 we could go either 1 spot or 2 spots. 3 we could go either 1 spot, 2 spots, or 3 spots. So a brute force approach would be to iterate over every single possible distance jumped until you reach the target, but that would have way too high of a runtime. Hmm. Okay, we could look and see our potential based on each jump. So like for the first jump, we have 2 options. Option 1, go to index 1 where 3 is. Or option 2, go to index 2 where 1 is. And then we could, our potential would be, it's only one further spot, but we can potentially go 3 more. So we have a potential of 4. Whereas here, we go 2 further spots, but we can only go 1 more from that spot. So we would have a potential of 3. But would this work long term? Because let's try to think of a counter example. Let's do like, go 2 or 3, but here we can go like 10, or no. So here we could go 10. So in this case, option 1, you would still get the potential of 4. Here you would get the potential of 3 still, but you could jump 1 more and get the potential of 10, so it would be 1, 2, 3 jumps. And actually, let's make it like 5, and then let's just do 5 ones at the end. 2, 3, 4, 5. Okay. So option 2, if you jump to the 1, you can go 1, 2, 3 all the way to the end. Whereas option 1 with the potential of 4, you would go 1, and then you could jump to the 5, 2, 3. Is that guaranteed to be optimal though? What if I do 3, 1, 2, 3, then you need another jump versus 1, 2, 3. You could get right there. Let's do 2, 3. So it's the same case as before. 2 to the 1. 1, 2, 3. To get to the 5. 1, 2, 3. And then that would be 1, 2. So I think this potential strategy might work. Let's try it out. Why don't I add these test cases just while we're at it? Might be interesting. I don't know that I came up with the best ones, but we'll see. So we want to iterate over the numbers. And then for every number, actually we might not want to do it this way because we might not want to go linearly. So let's just create a position variable. While position less than length nums -1. Let's create a jump counter. So we want to explore the possibilities at the current position. So the value at our current position is nums position, and then okay. So our possible locations would be from our current value +1 all the way to our current value plus the value of however far we can jump. So this for option, the case 2 and position 0, that would end up being 1 or 2, because we could end up either at 1 or 2, 3 or 1. So for all possible locations, and actually we don't need to take up memory for this, we can just do this. So for possible locations in that range, we want to calculate the potential, which would be, we can just call it, since we're just comparing these potentials relative to each other, we can just compare the position it'll get us to, or add the position it'll get us to, plus the potential to go further, so the actual number at that location. So in this case, for index 1, it would give us 1 plus the value at index 1, so 1 plus 3 is 4. And for index 2, it would give us 2 plus the value plus 1, because 1's at that position, which would give us 3. So then we'll do max potential, and we'll just set it to 0, and then max potential index. Let's set it to -1, just because. So if the potential is greater than max potential, then we will do max potential equals potential, and max potential index equals possible location. So then we actually want to end up jumping to that max potential index. So then pos equals max potential index, and then we have one more jump. Let's just run this and see what happens. What are we actually returning here? Returning the number of jumps. So let's return jumps. Run this. We might have entered an infinite loop, I'm thinking. Okay. I'm thinking definitely we did. Why is that? So we go. Let's add some prints here. So we'll print our current position, and then jumping to our new position. Let's see what happens. Actually, do prints work on time limit exceeded? All right, pos is 0. We're jumping to 1. Okay, that's true. Pos is 1. We're jumping to 3. 0, 0, 1, 2, 3. 0, 1, 2, 3, 4. It should be jumping to index 4 there. Assuming this is the right case, let me print the actual nums. I don't know why it doesn't show me what case it's timing out on. Maybe it does at the bottom. 2, 3, 1, 1, 4. So 0, we jump to 1. 1, we want to jump to 4, because we can. Okay, let's add a check here. If our possible location is our target location. So equals length nums minus 1. Then we can just return the current amount of jumps we've made plus that one additional jump. Let's see what happens here. Output limit exceeded. Okay, that's fine. Jumping to 1, 1 jumping to 3. I am going to actually make this list just to print it. Pos is positions, possible locations are. I think I need a new one at the end. So, okay, we have to jump to 1. 1, the possible location. Wait. Pos 0, possible locations. That's not right. Pos is val is the value should be 2 at position 0, which means we should be able to go. Oh, I see the issue. We're go 1 further than where we currently wait. So yeah, so we're at 0. Okay, but it's our potential. Wait, what? So we can go to index 1. Yeah, okay, so these are indexes. So this was right. We can go from index 1 to index 0 plus 2. So we can go from either index 1 or 2. That should be right. 2, 3, 1, 1, 4. Alright, but that should be when pos is 0. So pos is 0, our val is 2. And we should be able to go to either of those. So I'm not sure why it's saying we can only go to 1. Let's print this out. Invalid syntax, classic. Val is 2, our possible locations are 1. Oh, it's because ranges are exclusive at the end. Duh. Alright. Okay, so all of those cases were accepted. Do I trust that though? I'm curious what happens if I remove this. Works for those cases. I don't fully trust that, so I'm just going to leave that in there. Because there could be a case where the potential of some lower one is higher, but so you don't jump all the way there. I'm pretty sure. Alright, let's try submitting this. Oh, nice. It's accepted. And the runtime beat some others, but I don't know that that's actually very reliable. Awesome. Thanks for watching.